The next question, I'm not sure what year this came from, it was a question 9. Again, we've lost a wee bit of this over at the side, so I'll just read it out. A 100 microfarad capacitor is connected to a 12 volt supply. Calculate the charge stored. So we know Q is equal to CV, and therefore that's C is equal to 100 microfarads. I'm just going to write the micro in, and V is 12, and that gives you an answer of 1200 microcoulombs. Q is equal to 1200 microcoulombs. Show on the diagram the arrangement and magnitude of the charge on the capacitor. So you know that the negative side. So the next part of the question asks you to show on the diagram the arrangement and magnitude of charge on the capacitor. So there's two things you have to do there, and when you did this in your test, some of you forgot that second bit there. So this side of the cell is positive, and because it's positive, it's going to draw electrons off this side of the capacitor here, and they're going to move along here onto the positive side of the battery. And therefore, if electrons leave this, then this becomes positively charged. The electrons then from this side of the battery are going to be deposited onto this side of the capacitor, and so you're going to end up with an equal amount of positive charge in the other side, and it has got a charge of magnitude minus 1200 microcoulombs. This 100 microfarad charged capacitor is disconnected from the battery and then connected across. Now I've lost my across bit here, but when you see across, that means in parallel. Cross always means in parallel. Sometimes it will tell you that you know it's connected in parallel. It doesn't say this here. So if we just draw this, that's what you have there. You've got your 100 microfarads and a 300. So what happens to the charge initially stored on the 100 microfarad capacitor? Well, that charge is shared. So you have a total amount of charge here as a result of being charged to 12 volts, and that charge is shared. And so some of it moves on to the 300 microfarad capacitor. Calculate the new voltage across the pair of capacitors. So I'll just move the camera a wee bit here. Okay, calculate the new voltage across the pair of capacitors. What we have to do first of all is calculate our initial charge, and that's initial charge that's been shared by the 100 microfarad capacitor, but that's also the charge in the whole system because that's all that is available. So our initial charge, we're just using a 100 microfarad capacitor. I'll just draw that to the side, and it was charged to 12 volts. So that's how we're going to calculate our initial charge. Just draw it over here, or move it over. So Q initial is equal to C times V, which is 100 microfarads multiplied by 12, and that gives you 1200 microcoulombs. Then we are looking then for a total capacitance. So the total capacitance then is equal to, now these are in parallel with each other, so therefore you just add them. So it's 100 plus 300, and that's equal to 400. And then the last part of the question, or what we're really looking for, is our new voltage. So we're using our total charge and our total capacitance. So V is equal to Q over C. Sure you can see that. And that's equal to 1200 divided by C is 400. And you get an answer of 3 volts. Now that kind of question is really, really common. So if it says across or it says in parallel, then you have to first of all get your initial charge on your first capacitor, calculate your total capacitance, and then just use, these are all totals then, your total voltage. You remember that in a parallel circuit the voltage across each part is the same. Whatever voltage you get across one capacitor will be the same as the other. And so you're going to do that. So I'll just write that down again. You're finding initial charge, you're finding a total capacitance, and then you're finding a new value for your voltage by dividing Q over C. And that's how you're doing that. Right, the next question. A capacitor of 250 farads is placed in series with a 50 kilo ohm resistor connected to a 12 volt supply. State an equation for the time constant of the circuit. So that's just tau is equal to C multiplied by R. Using equations, now you could do this with base units, but equations are far easier. The base units for capacitance and resistance are quite difficult to work out, and it's very easy to make a mistake. So if you have an option, do use equations. So we want to prove that the right hand side has got the units of time. So capacitance is Q over V. Resistance is V over I. V and V cancel. That leaves you with Q over I. But of course Q is equal to I times T. And the currents cancel also. And therefore you've got tau, which is your time constant, is really equal to a time. And of course units of time are seconds. I'll just show you down there. And so you have proved that. Next question, calculate the time constant of the circuit. So we know tau is equal to C multiplied by R, and that's equal to 12.5, it's equal to 250, which is your capacitance, micro of course, and it's 50 kilo, so be careful. It's 250 by 10 to the minus 6, multiplied by 50 by 10 to the 3. And that gives you an answer of 12.5 seconds. Show that when the time passed is equal to tau, the value of the original current has reduced to approximately 37%. Now really this is a derivation of what the current has gone down to, or the charge or the voltage, depending on what the question's asking you. So we're being asked for current here. So write down your initial equation. I is equal to I naught e to the minus t over CR. And whenever the time passed is equal to tau, then that's equal to CR. We know tau is CR. So you're going to put that back into this equation. So I is now equal to I naught e to the minus CR over CR. But of course CR over CR is 1. So that gives you e to the minus 1. And of course e to the minus 1 is the same as 1 over e. And we know that e is equal to 2.72 to 3 significant figures. And when you put that into the calculator, you come up with a value of 0.367 times I naught. So that's what I is now equal to after this length of time has passed. And of course 0.367 to 2 significant figures, and as a percentage is 37%. And so you've proved this. And again, this is a question which comes up fairly regularly, and it is a question that you would really need to make sure that you can do. Last part of this question, calculate the time that has passed when the current is reduced to 20% of its original value. So we're going to write I is equal to I naught e to the minus t over CR. I, you're told, has been reduced to 20% of its original value. So I is now equal to 20% of I naught, but we have to write it as a decimal, 0.2 I naught. So we're going to put that back into this equation again. So 0.2 times I naught is equal to I naught e to the minus t. And we also know, I'm going to write it here, CR, we've done the calculation, is 12.5 seconds. And so therefore we're going to put that into 12.5. So I naughts go out. 0.2 is equal to e to the minus t over 12.5. To get rid of the e, we have to take the natural log of both sides. That gets rid of the e. And we're now down to that. And therefore, t is going to be equal to minus 12.5 times the log of 0.2. Now the log of 0.2 will come out as a negative number anyway, and therefore your answer will be a positive value. And whenever you do that calculation, t comes out to be equal to 20.1 seconds.